Welcome back to the Deep Dive. We're continuing our exploration of the OEIS, and today we're diving into A00078.
The Tetranacci numbers.
Right, the Tetranacci numbers.
A sequence that might seem like, just a simple step up from the famous Fibonacci sequence, but
Yeah.
it's got a lot more going on under the surface, connections to all sorts of math.
All right, so let's start with the basics then. For those who might not know, how do we define the Tetranacci sequence?
Well, you've got Fibonacci, where you add the two previous numbers to get the next one, right?
Right.
Tetranacci, we're doing the same idea, but we're adding the FUR previous numbers.
Okay, so instead of starting 0, 1, 1, 2, 3, 5, like Fibonacci.
You start with 0, 0, 0, and then a 1 for Tetranacci.
And what comes after that?
1, 2, 4, 8, 15, 29, and so on. Grows way faster than Fibonacci.
Yeah, I'm noticing that. Fibonacci kind of roughly doubles at each step, but these Tetranacci numbers seem to almost quadruple early on. Big difference.
Definitely. And it's all because of those extra two terms we added to the rule.
Now, I'm looking at the OEIS entry, A0000008. It's got formulas, references, links to all kinds of other sequences. It's packed.
That just shows you how much is hidden in what seems like a pretty basic pattern. It's not just the numbers themselves, it's what they mean in other parts of math.
That's what always gets me about the OEIS. It's like this map that shows you these hidden links between completely different math concepts.
Totally. Like, take the connection between Tetranacci numbers and combinatorics, for example. Emmerich Deutsch, a mathematician, pointed out that the nth Tetranacci number...
The nth? Okay.
Yeah, it actually counts all the different ways you can write n3 as a sum of 1s, 2s, 3s, and 4s.
So it's like if you had stamps worth 1, 2, 3, and 4 cents.
Huh?
The Tetranacci number would tell you how many ways you could combine those to get a certain postage.
That's it. A very down-to-earth way to picture what those numbers are actually measuring. And then it gets even cooler when you bring in binary sequences.
Binary sequences, those are just strings of zeros and ones, right? How do those fit in with Tetranacci?
Turns out that n plus 4th Tetranacci number,
Okay.
it also counts how many binary sequences of length don't have the pattern 1111 in them.
So no 4 ones in a row. Why is that connection important?
Because avoiding patterns in sequences, huge area study in combinatorics. This link to Tetranacci, through something as simple as not having 4 ones, opens up a whole new direction.
It's like the Tetranacci sequence is a key that unlocks these hidden doors in different mathematical realms. And I see there's also a link to geometry, specifically triangulating polygons.
Right. When you look at how you can triangulate certain polygons in this zigzag pattern,
Okay.
the ways you can pair up the edges without them overlapping, that number is a Tetranacci number. And the more sides the polygon has, the clearer the relationship becomes.
Fascinating. Feels like we're just scratching the surface of what these numbers can do. And for our more math-minded listeners, I know there's things like generating functions, even the Binet-like formula.
We'll definitely get into those next time. But even those more advanced concepts, they all come from that basic idea of adding 4 previous terms. Shows you how elegance and complexity can go hand in hand in math.
It definitely makes me want to see where this deep dive will lead us next.
Me too.
Okay, so let's get into some of the more complex stuff with the Tetranacci sequence.
Yeah.
You mentioned a Binet-like formula earlier.
Right.
Now, for our listeners who aren't familiar, Binet's formula, that's how you can calculate any Fibonacci number
Right.
directly, without having to go through the whole sequence.
Yeah.
Is there something similar for Tetranacci?
There is, but
Okay.
it's a bit more involved than Fibonacci's formula, which uses the golden ratio, very elegant.
Right.
The Tetranacci version, you have to solve a 4th-degree polynomial to find its roots, and those roots are part of the formula.
So it's like Fibonacci's formula, but
Supercharged.
yeah, more complex, but you can still calculate any Tetranacci number directly.
Exactly. It's a great example of how you can generalize and extend mathematical ideas, but the complexity ramps up pretty quick.
I'm also curious about those generating functions you talked about. How do those work with the Tetranacci sequence?
Generating functions are a really powerful tool in math. They let us represent an entire infinite sequence as a single function.
So instead of listing out the whole sequence, we can pack it all into one formula.
Yep. And for the Tetranacci sequence, its generating function is by 3, 1 by 2, by 3, by 3, by 4.
Wow, looks surprisingly simple for something that's representing an infinite sequence. What can we actually do with this generating function, though?
It opens up all these techniques from algebra and calculus. We can use it to derive identities for Tetranacci numbers or analyze how they behave as you go further and further down the sequence, their asymptotic behavior.
So it's not just a neat way to write it down, it actually helps us understand the sequence more deeply.
Exactly. It's a perfect example of how mathematicians condense complex information into elegant forms and then use those forms to uncover hidden properties.
Before we move on, we have to talk about prime Tetranacci numbers. Finding prime numbers within a specific sequence is something a lot of people are interested in.
Yeah, and the OEIS is the best place to explore that. Entries A1U4534 and A1U4535 are all about prime Tetranacci numbers.
So A104534, that one lists the positions, the indices where you find prime Tetranaccis, right? And A1044535, that gives us the actual prime numbers themselves.
That's right. The first few are 2, 29, 401, 773, and then it jumps to a pretty big number, 53502200959. You can see they get less frequent as you go along.
Makes you wonder how mathematicians even find these prime Tetranacci numbers, especially when they get so large.
It takes some pretty sophisticated algorithms and computational techniques. They often use properties of both prime numbers and the Tetranacci sequence itself. As of 2009, research had only identified prime Tetranacci numbers up to index 100,000.
So beyond that point, there's a whole bunch of potentially prime Tetranacci numbers just waiting to be discovered. It really shows you the vastness of number theory.
And the excitement of ongoing math research. Even with sequences like this, where the rules are well defined, there are still mysteries to solve and patterns to find.
Speaking of finding patterns, the OEIS entry is full of formulas and identities for Tetranacci numbers. Looks like mathematicians have been busy connecting them to other mathematical concepts.
Mathematicians are always curious, right? Like, take how you can use matrices to generate Tetranacci numbers. The OEIS entry shows how to express the nth Tetranacci number using a specific 4x4 matrix raised to the power of n.
So now we're connecting Tetranacci to linear algebra. Amazing how many different areas of math we're touching on here.
And that's just one example. You'll find formulas relating Tetranacci numbers to binomial coefficients, combinatorial objects, all sorts of things. It's this whole web of interconnected mathematical ideas.
It really highlights how exploring even a single sequence can take you on these amazing journeys through different parts of math.
That's the beauty of the OEIS. It's not just a list of sequences, it's a roadmap that shows you how everything in math is connected. And today, with our deep dive into the Tetranacci sequence, we're seeing that firsthand.
This has been a really enlightening exploration so far. I can't wait to see what other insights are waiting for us in the last part of our deep dive.
There's still a lot more to uncover, especially when we think about what happens when you generalize Fibonacci-like sequences even further and the new research areas that opens up.
Sounds like the perfect way to wrap up our journey. Let's continue this fascinating discussion in part 3. All right, welcome back to the deep dive. We've spent quite a bit of time exploring these Tetranacci numbers, their links to combinatorics, geometry, those prime Tetranaccis.
Yeah.
What I'm thinking about now is like the bigger picture. What's really interesting about the Tetranacci sequence is it's not just some one-off thing.
Right.
It's part of a much larger family, the n-step Fibonacci sequences. So we're generalizing the whole concept even further. Instead of adding 2 previous terms like Fibonacci, or 4 like we did with Tetranacci, we could add any number of previous terms to get the next one.
You got it. You've got Fibonacci where you add 3, Pentanacci adding 5. You can just keep going. And every time you add another term, things get more complex. It's like opening up these whole new areas to explore in math.
Makes me wonder, though, what's the point of studying these more general n-step Fibonacci sequences? Or just making things more complicated for no reason? Or is there something deeper going on?
That's a good question. And it's something mathematicians are actively working on. One thing they're looking at is how the properties of these sequences change as n gets bigger. Like we saw with Tetranacci, the formula for calculating any term directly, it's way more complicated than Fibonacci's, right? It involves those roots of a 4th-degree polynomial.
Right.
So you go to Pentanacci, Hexanacci, and those formulas are going to get even crazier.
They do, yeah.
But by analyzing those formulas, understanding their structure, you can learn a lot about these generalized sequences. It's like peeling back the layers of an onion, uncovering deeper mathematical truths.
Makes me think of those generating functions we talked about earlier. Each n-step Fibonacci sequence, it would have its own special generating function, right?
Absolutely. And by studying those generating functions, you can spot patterns and relationships that you wouldn't see just by looking at the sequences themselves. It's like having a different perspective, a new lens to look at these mathematical objects through.
So it's not about adding complexity just for the sake of it. When we look at these more general sequences, we're potentially uncovering some fundamental mathematical principles.
Exactly. It's all about the power of generalization in math. You go beyond specific examples, look for those broader patterns, and suddenly you have a deeper understanding of the underlying structure of the mathematical world.
I think that's a great point for our listeners to take away. Our deep dive into Tetranacci, it's shown us that even the most basic mathematical patterns can have incredible depth and lead to unexpected connections.
And that's the key. That spirit of exploration, going beyond what's familiar, that's how we find those hidden mathematical gems. Who knows what's waiting for us out there as we keep exploring the OEIS and the fascinating world of n-step Fibonacci sequences.
A perfect thought to end our deep dive on. Thank you for joining us on this journey into the world of Tetranacci numbers. Keep exploring the infinite wonders of the OEIS.